love writing on the blackboard. Personally, I just love writing in chalk on the blackboard. But as we've been virtual, I realized, you know, I don't know, I guess through the whole pandemic, I've realized how valuable it is for you all to have recordings of class. And a lot of students have told me that they really appreciate having recordings of class they can go back and look at later. And of course, when we're virtual, it's just easy to do that. I just hit record. Even when we were in person, you know, when it was last spring, when it was hybrid, there were like all these cameras set up in multiple places, so I could like actually record the blackboard. But that's hard to do now. And you know, the classes that we did in person, like there's not recordings of it. I realized, I think I'm just gonna, instead of writing on the board, I'm just gonna write here on my screen. I've got this nice little like, you know, tablet thing with it. So, but that way there will be a nice recording of it for you later, and even like the PDF of what I wrote will be available. So, that's what I'm thinking to do. All right. So we left off last time with this question of so that symbol is the kind of 0 with the slash there, it means the empty set, right? And we said, is the empty set a subset of something else? Say, the natural numbers. But the natural numbers, it doesn't matter in particular. Really the question is, I mean, you could ask the same question about, you know, lots of other sets. Is the empty set a subset of those things or not? And so we kind of took a poll, and it was kind of split. So does anyone want to argue or, you know, give a reason that why they think either this should be true or false? So I guess I should be ready.
I said false.
Okay.
Because the way I saw the empty set, it doesn't have any elements of natural numbers.
It doesn't have any elements, right? Okay, so there aren't any natural numbers in the empty set, so it shouldn't be a subset of natural numbers because, okay, yep. So maybe, you know, I'll put here like, if there are no elements of natural numbers in. Garrett, did you have your hand up?
Yeah. I was just going to say, since we know that, like, if you have a set that is like 1, 2, 2, 2, 2, 3, all of those twos kind of get squashed together,
right?
As far as that's concerned.
Yeah.
And so to that extent, like, the natural set of natural numbers, like, has a whole bunch of empty spots essentially that are just not there. At least that's how I would be thinking of it, and why I think of, like, it does contain it.
Okay.
That might
So
not
you
make
think-
sense, but that's just how I get it.
Right, so this is kind of a counterpoint to Mason's argument. You're saying, well, it kind of does contain some natural numbers, like, sort of in the sense that maybe the natural number set has some not there things in it. And it's, you know, I mean, it's weird to say, but I think I understand what you're saying. Okay, I don't really know how to write that down, but okay, we'll note it. Anyone else have any arguments why? I'm going to need to write bigger, aren't I? That's very small. Okay. It's different when you're like looking at it on your screen versus when it's up here. I will write bigger. You know what I do. Matthew?
It doesn't contain elements that aren't natural numbers.
It doesn't. Yeah. So it doesn't contain elements that aren't natural numbers. So maybe that means. So you're saying yes. Okay. So it doesn't contain any elements that aren't. So you're saying, like, you know, when would something not be a subset? Like A is not a subset of B if A has some things that aren't in B. Right? But you're saying, well, that's not true. That's not the case here. The empty set doesn't have anything that's not in it. It doesn't have any elements at all. So maybe it should be a subset. Okay. Any other thoughts, arguments why it should or shouldn't be? Yeah, fine.
If we assume the empty set isn't a subset of the natural numbers, then inevitably there's going to exist an element in the empty set that isn't in the natural numbers. But that wouldn't make sense because the empty set.
Okay, so that's similar to, I think, what
Yeah.
Matthew was saying, right? You're saying, like you're kind of saying that you want to define what it means for something to not be a subset as there has to be something in there that's not in the other set, and that doesn't make sense in this case. Okay. Anything else? So, let's go back to the definition of, let's go back to the definition of subset. What does it mean for one set to be a subset of another set? So the definition of subset, right? By the definition of subset, this means for all, A in the empty set, A is an element. So for every element of the empty set, that A is also an element of the natural numbers. Right? This is how we define subset. Every element of one thing is in the other thing. So that then raises the question, what does this mean? Right? What does it mean, what should it mean to have a Forall where the domain is empty? Right, so what does / should it mean to have a Forall with an empty domain? Am I writing big enough now? There's in the back, you see, yeah. So, there's a few different ways to think about this. One way to think about this is if we go back to, I think we thought about things this way when we were thinking about, what should implies mean when a premise is false. Think about if someone makes a Forall kind of statement to you, when have they lied? Right? When have they told you something that wasn't true? So if I say, every February the 37th, I fly to the moon. Did I lie to you? Do you think yes? How do you know I lied to you?
There's no such a thing as the 37th.
Yeah, well, right, there's no such thing as February the 37th. But I didn't say there is a February the 37th. I just said every day, for all days that are February the 37th, right? Every February the 37th, I fly to the moon. So it's a silly statement, right? It doesn't necessarily feel true. I mean, but I didn't lie. I would say I would claim I did not lie to you, because indeed every single time that it happens to be February the 37th, I do indeed fly to the moon. But of course that never happens. So, and the only way I would be lying to you is if there actually was a February the 37th and I didn't fly to the moon, right? Or if I say every green dog I've ever met has been 37 feet tall. Right? Well, I've never met any green dogs, so it's not a lie, right? It's actually true that every green dog I've ever met, that is not a moon, has been 37 feet tall. So one, make a false statement about. Okay, here's another way to think of it. So remember, if I say like for all, so this is what we had before. This is the same as, right, we have this way to like write a for all with a different domain, but then kind of restrict it again using implication. So I could just say, I could pick any domain I want. I could say, you know, for all A in some domain D, if A is in the empty set, then A is in the natural numbers. Okay, these are equivalent. Right, here I have my domain as empty set, and here I have some bigger domain, it doesn't matter what it is, but I restrict it again to only talking about the empty set by putting this implication here. You have a question, Adora, or you just mentioned? What was that?
I did have a question, but,
Okay. Well, and is this true? So, this right here, this is always false, right? Because the empty set is empty, so there can never be anything that's an element of it. So this is always false implies something. And we argued before, right, for kind of similar reasons, that false implies anything is true. So in a sense, a for all with an empty domain should be true for kind of the same reason that false implies something should be true. Okay, so this is false. And false implies anything is true. I think I had one more reason. I don't remember what it was. Oh, I know what the other reason was, but I'm not gonna say that one, but we'll come back to it later, because it's gonna make more sense later. Okay. So, this statement, because it's a for all on an empty domain, is true, and therefore, this is true. Check. Now, I want to be clear what I'm saying. I'm not saying that like we'll get into a little bit of math philosophy here, right? Usually when you're learning math in elementary school or whatever, you're just told like this is the way it is, right? This is how the world is, and you have to do it this way, right? That's not really how math works, right? It's not like God came down with some stone tablets and said, like, here is math, you must do it this way, right? Like, from one point of view, math is something that we as humans just make up, and we can kind of do whatever we want. From another point of view, though, there's certain ways of doing things that seem to work out much more nicely than other ways of doing things, right? So even though we could do whatever we like, we find that some ways of doing things seem better than others, right? So what I'm not saying is this is the way it must be, or this is the way it is. I'm saying it turns out that defining things this way makes everything work out very nicely. If we defined it the other way, we could do that. We could define it that way, and we could see what the consequences are. But the consequences turn out to be not as nice. We'd have weird special cases everywhere. We'd have to always say like, oh well, if it's not the empty set, then blah blah blah. But if it's the empty set, then we have to say something else that's special about the empty set, right? But if we define it this way, a lot of things we can just say that work for all sets, and they naturally include the empty set. So yes, the empty set is a subset of any other set, because it is true that every element of the empty set is in the other set, because an empty Forall kind of doesn't say anything, so it's just like, sure, that's true. Okay. And if you don't believe me now, that's okay, because as we continue on throughout the semester, I think there will be several places where I'll point out other places where we'll see, see, since the empty set is a subset of this, that makes this nice. And if it wasn't, see how it would be annoying, right? And you'll see that happen multiple times. Okay, so now we got that out of the way, I want to talk about some operations on sets. Okay, and we'll start this today. I don't know if we'll get through all of them today. That's okay. We'll continue. We'll pick up wherever we leave off. So the first thing I'm going to show you is something called Cartesian product. Okay, here's the definition. Doesn't really need to be numbered, but so if A and B are sets, the Cartesian product I think it's called the Cartesian product because it's named for René Descartes. And why Descartes has a specific math thing named after him. I have a guess, but I'm not going to say it because I'm really not sure. But you can look it up later. Cartesian product of A and B is, what is it? It's the set. So it's another set. We take two sets in and we do this operation on them. We get a set out. It's the set of all possible ordered pairs of elements from A and B. Okay, that is one way we could write this. The way we write Cartesian product is with a little like times X symbol thing. Sometimes we say A cross B, or you can say A times B, either one. So it's the set of pairs A comma B such that A is an element of A and B is an element of B. Okay, and implicitly, when I have multiple things over here like this, like multiple kind of conditions, it means you kind of do these in all possible combinations, right? All possible ways. So every possible A and B where A is in big A and B is in big B, we're going to include. So as an example, let's see. There's a keyboard away. That's annoying. We should bring my own keyboard. Interesting idea. The thing that's annoying is that when I want to show you something in Disco, I've got to like flip this around and use the keyboard. Just instead of writing an example, I'm going to show you an example in Disco. So Disco does not yet have the Cartesian product operator built in, but we can still do it by writing. So I could say like, A comma B such that A is in 1, 2, 3, and B is in true, false. And so what I get out, actually this off. Sorry. Right, I get a set of pairs, right? And I get every possible combination of, you know, a number from the set 1, 2, 3, and a Boolean from the set true and false. So I get 1 and false, 1 and true, 2 and false, 2 and true, 3 and false, 2 and true. Make sense? Okay, one way to think about this, so we can think of this in terms of filling out a 2D grid. So like, you know, for example, if my set A is, you know, 1, 2, 3, and my set B is true, false, I can make this little table like this where the rows are labeled by elements of A, the columns are labeled by elements of B, right? And each, you know, so this is 1, comma, true. This thing here is 1, comma, false. This is 2, comma, true, 2, comma, false. Right? The thing in each cell is the pair of, you know, the label on the row and the label on the column. Okay, but I don't keep them in a table like that. I throw them all in a big set. And okay. So can anyone tell me in general, if I have a set, you know, if I have two sets of certain size, right, a certain number of elements in each, and I take the Cartesian product, can you say something about how many elements will be in the Cartesian product? Medora?
The size of each times, or the product of the size.
Right, exactly. And hopefully, thinking about it in terms of this rectangle should make that clear, right? I've got 3 rows because I had 3 things in this set. I have 2 columns because I had 2 things in this set. And so then the area of the rectangle is just the product of, you know, 3, in this case, 3 times 2. So in general, the size of A cross B is the product of the sizes of A and B. And we can actually, so we often use this notation for the size of a set that looks like an absolute value thing. Which you might think that's weird. Why do we use that for both absolute value and for the size of the set? Actually, absolute value really is a kind of size. So the absolute value of a number is the size of the number in terms of how far away it is from 0. So like, the farther away from 0 you are, the bigger it is in some sense. And so, in some way, it's actually a very kind of similar use. You use the absolute value symbols to talk about size. So, right, I can even write it like this. If I want to use, like, it's not as common to use this X symbol for talking about multiplication, but it looks nice. I write it that way, right? So, you know, S is the size of S. Okay. And you can use that notation in Disco as well. You can use the like vertical bars when we talk about size. Yes?
So then this probably would work the way that it like feels like it should with the empty sets, right?
Say that again?
This works the same way we like expect it would work with the empty
Oh
set.
yeah, no, good, very good point. I hadn't even thought of that. Yes. So let's think about the empty set, right? Does this kind of make sense? Does this work? Well, what is, let's see the page. So what is empty set across, 1, 2, 3? Well, it's the set of all possible pairs where the first element is an element of the empty set, and the second element is an element of 1, 2, 3. Right? How many such pairs are there? there aren't any elements of the empty set, so I can't make a pair where the first element is an element of the empty set. So all possible ways to do that is none. Right? So it is the empty set. Right? And I think as Garrett was pointing out, this actually is still, this works. When we think about, this works. We think about, oops, you know, right? I claimed that this should be true for any sets. And it works in this case, right? Because I said that this thing is the empty set, so the size of that is 0. And well, this is the size of the empty set, it's 0 times 3. Well, 0 times 3 is 0. Right. So the empty set is kind of acting like 0 in that case. When you multiply by it, it kills the other thing, right? Just like multiplying by 0 kills whatever else you get. Okay, good. Okay. Next one I want to talk about, it's kind of fun. I don't remember why I put it in this order. I think I had a good reason for it. Let me go with it. So this is the, I guess it's number 2. This is called a power set. Definition. The power set of a set A, written, so sometimes you'll see it written like with this kind of like this fancy scripty P. Right, or I'll say it's just written power. Right, you don't write the fancy scripty P in this, but you just say power. What is it? It's the set of all possible subsets of A. Whoa, it's a set of sets, yes. You can do that, right? Nobody said sets can only have numbers in them. Sets can have anything you want, including other sets. So let's do an example. So let's again choose, 1, 2, 3. Then what is the power set of A going to be? It's a set. Okay. What are some subsets of A? We'll just list them out. What are some different subsets we could have of A? One. Just one by itself. I agree. That is a subset. Cool. What else? What was that?
3.
Just 3? Okay. Yep. Any more? Garrett?
The empty set.
The empty set. Yes. The empty set is a subset of anything, right? So that counts. What else? Adora? 1 and 2 together. Agree. Any more? Happy. 2. Okay, yeah, got 2 by itself. Any more?
2 and
2 and 3. Yeah. We have to start being careful that we don't, like if someone said, oh, how about 2 and 1? Well, that's the same as 1 and 2, right? So, Adora?
1, 2, and 3.
Yeah, so 1, 2, and 3. Right, we talked about this when we defined subsets, that any set is a subset of itself. Right? Are there any more? 1 and 3? Did we already do that one? No, I guess we didn't. Okay. Any more? Mason says no. How much money are you willing to bet on that? None. None. Okay, that's fair.
I don't really either, I just.
Okay, going once, going twice. Okay. You're right, that's it, there's no more. Good. So that is the set of all possible subsets. But how do we, how do we know that we got them all? Right? Aside from kind of thinking hard and being like, well, I can't think of any more, so I'm pretty sure, there's not any more. In this case, yeah, we could probably do that and convince ourselves, yes, we got them all. But, and maybe you could kind of systematically go through and be like, well, there's an empty set, and there's some that only have a single element, and there's some that have two, and, you could kind of convince yourself that it exists more. But how can we be more systematic about it? Here's an interesting way to think about it. So notice that every time we make a subset, I can look at this set, and for each element, I can independently choose, do I want to have this one in my subset or not? Right? So I can say, do I want one in there or not? No, I don't want one. How about two? Do you want two? Yeah, let's take two. How about three? Yeah, we'll take that also. Okay, well, we just described this subset. Right? But if I had made some different choices, maybe I said, yeah, I do want one, but I don't want two, and I don't want three. Okay, well, that gives me this subset. Right? Every possible way I can choose, make choices like that, will give me one of those subsets. So, we can systematically list all subsets by, let's say, independently choosing whether or not to include each element. Okay, so I'm going to make a little table here. Okay, and each column I'm going to put whether or not I chose I'm going to put whether or not I chose each element, and then I'm going to write the resulting subset on the right. Okay? So, right, what I need to do is list every possible combination of choosing or not choosing each of 1, 2, 3. This is just like making a truth table. Okay, so for example, I can say, false, 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 true, 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 and then for 2 I'm going to say false, false, true, true, false, false, true, true, and then for 3 I'm going to say false, true, false, true, false, true, false, true, right? That's all the possible combinations of picking or not picking each element, right? And then for each one of these corresponds to a unique subset. So if I don't pick any of them, I get the empty set. Right? If I don't pick 1, I don't pick 2, but I do pick 3, well, I get just 3 by itself. This is just 2 by itself. This is 2 and 3. This is just 1 by itself. This is 1 and 3. This is 1 and 2. This is 2. Okay, so another way to think of this, right? So each subset of, in this case, the set 1, 2, 3 corresponds to a string of 3 bits. Right, where a bit means like a 0 or 1 or a true or false, right? I've written them here as trues and falses, but you can also think of them as zeros or ones. So, how many strings of 3 bits are there? Good. There are 8, right. In general, if I have a string of n bits, how many possible strings of n bits are there? Sure? 2 to the n. Why is it 2 to the n? You're right. You know, yeah.
Just the two possibilities are true and false.
Right.
So, true and false.
Exactly, that's right. Yeah, so because for each of those n things, I get to choose true or false. And so I have 2 choices for this one, and 2 choices for this one, 2 choices for this one. And I multiply all those choices together. So in general, there are 2 to the n bit strings. Right? Hence, in general, we can say that the size of the power set of A is 2 to the power of the size of A. Right? In this example, A had 3 elements, and the number of possible subsets, right, corresponded to all the length 3 bit strings, and there's 2 to the 3 of those. And notice, right, this is a really nice, simple, elegant formula, right? And just the idea of listing all possible combinations of trues and falses to get all the subsets, that's also a very elegant, simple idea, right? And this is another way, this is another place where we see, like, the universe really wants the empty set and the whole set to be considered subsets. It'd be weird if we said, no, the empty set is not a subset. Well, now it's like, well, we say, oh, it's every possible combination of bits, oh, but not all false, because that would give you the empty set, and we don't want that. Right? It's like, well, why exclude that? Because that seems a natural, it seems naturally included in this definition, right? We would have to make the definition longer and more complicated if we wanted to leave it out. Right? And then we'd have a formula like, oh, 2 to the n minus 1, because we don't want that empty set. No, we include it. Right, and then also, we talked about how, you know, in English, the way we use the word subset, we often use it to mean something that's actually smaller, right? You wouldn't have the entire set be a subset of itself. But, I mean, we could make a word for that in math, and it doesn't really matter what words we use, but again, this is showing us that sort of the simplest concept of subsetness is the one where sets are subsets of themselves. And so if we're going to use a simple word for some concept, we would like to use the simplest word for the simplest concept. And then we can make up other words like a strict subset if we want to say it's not equal to, you know, we don't include the set. All right. Here's a question for you. The power set of the empty set. What do you think? The empty set. What do y'all think? Does that make sense? So the power set, again, right, means the set of all possible subsets of that thing. So what are the subsets of the empty set? What are all the possible subsets of the empty set? Does it have any? What was that?
The empty set.
Yeah, so it is a subset of itself. Right? Any set is a subset of itself. And for that matter, the empty set is a subset of anything. So is a subset of the empty set. Are there any others? No, that's it. Okay. So, what this shows us is that the empty set actually has one subset. Right? So the answer is not the empty set. It is the set containing the empty set. It's a set of one thing, which is the empty set. Because the empty set has one subset. So it's a set containing the empty set. Yeah, I mean, this gets a little mind-bendy for sure. But you'll see how that's not the same thing as the empty set. The empty set has nothing in it. This thing has one thing in it, and that one thing is the empty set. Okay, and if we look at this formula, this makes sense, right? The size of A is 0. What's 2 to the 0? It's 1. I have one way to make no choices. Right? I don't have anything to choose, like whether it should be in or out of the subset. So there's only one way that I can just like sit there and do nothing. So, 2 to the size of the empty set is 2 to the 0. So whenever there's a definition involving, sets or something, and we've already seen this, and it's a good general principle, right? You should always try the empty set and just see what happens. Like, does it make sense with the empty set? Or try, like, just have a few sets that you try out and, like, see if it makes sense. I should say, actually, I should add something important. For finite sets. Right? This whole time we've been talking about finite sets, but when we introduced the idea of a set, I said, well, they could be infinite. So, it's certainly, whoa, that's cool. Oh, I like it too. It's certainly possible to talk about the power set of an infinite set. You'll just have infinitely many subsets. That's fine. What we can't really talk about yet is we don't really know what it means to talk about the size of an infinite set. And this formula doesn't really, it doesn't feel like it necessarily means anything for infinite sets. So this is just for finite sets. All right. How much time do we have? 2 minutes. Let me just finish out by showing you our set in Discord. Okay. So I can ask for the power set of, say, like 1, 2, 3. Right, that's the same thing that we came up with before. It's probably in a different order, but order doesn't really matter. What order is it in? I don't even know. Oh, I guess it's right. It's sorting them. It has a specific idea of when one set is less than another set, and so it like puts them in order. But so notice like all the sets that have 1 in them come first. Well, the empty set comes first, and then whatever. It doesn't really matter. The order doesn't matter, right? I can ask for, the power set of the empty set. And indeed, right? That's not the empty set. That's the set containing the empty set. And if I ask for the size, so I could say, what's the size of the empty set? It says 0. If I ask for the size of the power set of the empty set, it says 1. I can also say, okay, what is the type of this set 1, 2, 3? It's a set of natural numbers, right? But if I say, what's the type of the power set of 1, 2, 3, what do you think it's going to say? Any ideas? Matthew?
Is it going to nest set of natural numbers like this set?
The set of, right, it's going to nest it. Exactly. It's a set of sets of natural numbers. Right. And I could keep calling powers on it. I don't want to do it too much because it gets very large, right? Because, like, the power set of 1, 2, 3 has 8 things. The power set of that would have 2 to the 8, which is power set of that would not fit in the universe. So, you know, gets big quick. But I could also do like, you know, what's the power set of the power set? Well, so before we, like, how big do you think this is going to be? So we know the power set of the empty set has one thing. So how big should the power set of the power set of the empty set? Garrett?
It should be times 2.
Yeah, it should be 2, right? It's a little hard to, I mean, it's definitely going to be 2. It's maybe a little hard to think about what those 2 things are. But it's the empty set and the set containing the empty set. Yeah. Again, yeah. You want hours of fun right here. No, okay, but thank you. This is why we're glad we have computers, right? Because computers aren't fazed by that. We just get tie ourselves in knots. Adora.
What's the type of the empty set?
The type of the empty set, that's a very good question. It says set A, and this little A means you can put any type you want in there. So it's like, I don't care, I can be a set of anything. And that makes sense, right? Because since there's no elements in it, it's not constrained to a particular kind of element. Yeah, we'll see more about this later. Like, we can have types where there's kind of holes where we can fill in whatever type we want. Called polymorphism, but we'll talk about that later. Any other questions? All right. So there's going to be a new module posted sometime later today. I'm not quite done with it, but I'll probably send out a message once it's posted, and it'll be due, you know, next Friday.